is not here yet. Ricky is. Ivory is not here yet. Juan is. Yeah, okay. Angelo is. Shakina is not here yet. Lauren is here. Jasmine's not here yet. Will is here. King is here. Yeah, I got it right. And Davis is here. Good deal. Now I have something wrong here. Yeah, okay. I have it right. I got to do this. Okay. Got it. Okay. We are recording. I should have gotten the roll mark before we started recording, but I guess it doesn't hurt anything. We'll start from current slide. Okay. All right, before we get started today, let me explain just a few things in case some of you are beginning to wonder. I've been named to a search committee or screening committee for candidates for a biology position here, as if I had time for that this summer. The only time I have available is from 10 to 12 on Tuesday, Thursday, and from 3:30 to 5:15 on Tuesday, Thursday. That's all. Monday, Wednesday, I have no time at all. And yet, I'm on this screening committee. And that took half of my office hours yesterday. From 3:30 on, I was screening. And I will probably take all my office hours on Thursday, tomorrow. I have no office hours today, so I can't get anything done today. So I'll hope to finish the screening part on Thursday. But why am I telling you this? Because even though I've got some of your papers graded, I don't have them all, and I certainly don't have them in Blackboard yet. And I've got to get the screening done before I can get back to doing those regular things, because everybody else has done it. And the dean said, oh, just look at mine and do it. Well, I've screened 3 people so far, and 2 out of the 3 they had wrong. So I went, yeah. So I can't just look at hers and say, oh yeah, I'll sign off on this, because they were wrong. They didn't meet the requirements when they said they did, and they just were being careless, I think. But that's why they put multiple people on the committee. So I can't just sign off. I've got to go through and look at all the applicants. So if you don't see your grades pop up right away, that's why. So I hope to finish screening. If I don't finish screening tomorrow, I'm sort of praying for rain on Friday so I can get some stuff done at home. Otherwise, my wife has a honey-do list about a mile long, so I just as soon, if I can get that finished Friday, then that would be great. I'm hoping to finish it tomorrow, but the likelihood of that is low. They've gone to a new thing online, and the system keeps crashing, so it takes a lot longer than it did when we did it by paper, but it saves them work, so they don't care. Okay, anyway, any questions, anything we've covered so far? We're on in chapter 3. See, I didn't count. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 2, 4, 6, 8. Yeah, I got it. Everybody counted for it. We're in chapter 3, differentiation. To me, the core chapter for this course. The rest of it is fluff. The limits we had to do ahead of time. What we'll do later is, adding to it. But this is the key chapter. Get this down. You got the core of Calculus 1. Okay? We're in section 3.4, rates of change. And we're on example 5. So no questions for anything prior to this? Okay. A truck enters the off-ramp of a highway at t is equal to 0 seconds. So let me get my pen activated here. Truck enters off-ramp, on or off? Off-ramp. T equals 0. That's where we're starting. Its position after t seconds, so t is in seconds, okay, is position is s. S is a function of time. Now, you tell me, you think this is going to be an increasing function, decreasing function? Just from the problem. Truck is entering an off-ramp at time t equals 0. Its position is the position. Okay, I sort of cheated on that. It is increasing because the truck's not backing up. Okay, position is increasing. Guess what's not increasing? The speed. The velocity is decreasing. Okay, and the acceleration will therefore be negative as well. So let's see. S of t. It's a really ugly S, isn't it? Okay. Its position t seconds afterwards at S of t. And here's Shekinah. Okay. We're on page 145, example 5. S of t is equal to, I was going to make that S look a little better. I didn't do a very good job of it, did I? Okay, let's see if I can make that look more like an S. The trouble is there's a little thing, I'm left-handed, and the little thing interrupting. That's not better, but I think I'll leave it alone. Okay. That's an S there, by the way, by definition. S of t is equal to 25t minus 0.3 t cubed. Okay? And this measured in meters, so the S is in meters. Okay? And this is good for 0 less than or equal to t is less than or equal to 5. And that, remember, is in seconds. Okay? The A part of this problem says, how fast is the truck going at the moment it enters the off-ramp? How fast? When does it enter the off-ramp? At t equals 0. How fast is the truck going at t equals 0? Now what's going to tell us how fast? What answers that question? Say that again. What answers the question, how fast? What are we looking for to answer that question? What quantity? Velocity, of course. How fast? That's your velocity. That's a position function. How do we get a velocity function out of a position function? This is one of those questions. Take a derivative. All right, yes. Take a derivative. Because v of t is equal to s prime of t, the first derivative of your displacement. And what would that be? Help me. A little louder. 25 is a good way to start. Minus. Yeah, please tell me you could do that. 0.9 t what? Squared. Very good. There's your velocity function. But we're interested in how fast it's going at t equals 0. So what do? Plug in 0. V of 0, and that's going to answer our question here, is going to be what? Say again? 25 what? Look at your units. Meters per second. Very good. So the answer for this is right there, 25 meters per second. Okay? That's the A part. The B part. Is the truck speeding up or slowing down? How can you tell that? Is the truck speeding up or slowing down? Why? Yeah. Why do you answer it that way?
Because if it's coming up a ramp, you have to slow down.
Okay, yeah, I understand that physically. I want the math answer. I already asked you that one. Does what's on the board let you know that?
You're subtracting.
Yes, exactly. For any subsequent t, and t only increases, it doesn't decrease. For any subsequent t equal 1, that's going to be a smaller number because when you square 1, you get 1 minus this. So that after 1 second, it'll be 24.1 meters per second. After 2 seconds, it will be 2 squared is 4 times 0.9 is 3.6. So that will be 21.4 meters per second. After 2 seconds, I already said that. 3 seconds, this will be 9. That would be 8.1. And 8.1 from 25 is 16.9 meters per second. 4, this would be, you get the general idea. I'm sort of a cynic. I want to make sure what happens with 5. When you square this, you get square 5. 25 times 0.9 is going to be a number less than 25. So you're almost going to be at 0 after 5 seconds. And this isn't good any further than 5 seconds. That's your domain. You can't go outside the domain. So that looks reasonable. Slowing down as you go. All right. Now, they showed the graph here, and notice that, and remember, that function is only good for, now they showed the velocity function here. That function up there is only good for t between 0 and 5, so your velocity function is only good between 0 and 5. It gets you down to a very slow speed, but you're not at a complete stop. What happens after that, I don't know. It may be that he rolls through the thing and merges onto the highway. It may be he comes to a complete stop. We don't know. This is only good 0 to 5 seconds. Okay? Now, this is a little beyond what we're doing here. But that question, is the truck speeding up or slowing down? Can anyone think of another term you might use there? If you're in your car and you're speeding up, what are you doing? Accelerating. Does anyone know what acceleration is? Physically.
What's the question?
Say again?
What was the question?
What is an acceleration? Okay, I'll phrase it this way. How do we get an acceleration? That's one of those questions. Take a derivative. She got it. Okay. Well, what do you take the derivative of? The acceleration is the time rate of change of what are you doing when you're speeding up? You're changing speed. Changing speed is change of speed with respect to time, right? That's acceleration, right? Or when you're slowing down. There's the break there. When you're slowing down, you're changing speed with respect to time. So it's dv dt, actually changing velocity with respect to time. So what would happen if you had done it that way? And that would have been perfectly correct. You haven't gotten there yet. Acceleration as a function of time is the first derivative of the velocity as a function of time. And what would that be? I don't think it's that hard. Well, how did you get that? The derivative of 25 is 0. I concur. Is that all your velocity function? No. Okay. Go back to the v of t, not v of 0. V of t. Because this is the first derivative of v of t. Okay, I agree 1.8 is in there. T is in there. Oh, a negative sign, that's in there too. So this says the acceleration is a negative 1.8 t, but t is always positive between 0 and 5. That's all it's good for, so therefore the acceleration is negative, meaning you're slowing down. Okay? Now that was extra, no extra charge. We haven't done that yet in the class, but you will be doing it in the future sometime or another. Okay. Now, any questions on that? So far we've been doing horizontal motion, even though our first figure had them going up. That wasn't vertical motion. Is that they had the displacement in the vertical axis, time on the horizontal axis, because time was the independent variable. But now we're going to do motion under the influence of gravity. So guess what direction that's going to be? It could be up. It could be at an angle. Well, where is your change coming from now? What gravity always do? Pulls you down, exactly. So the motion under the influence of gravity. Good old Galileo, and by the way, he would be a potential paper topic. And by the way, has anyone already chosen him? I don't remember. Okay, so he is a potential paper topic. See, I'm teaching 3 math classes and 2 physics, 1 physical science class. I can't keep straight who's taking. Somebody's writing on Galileo, but it's not in this class. Okay. But he discovered that the height S, the height S of t, now this is vertical motion, so this is going to be height. Okay? The height S of t and velocity v of t at any times t is in seconds, okay, of an object, and this time we're tossing it vertically into the air. Now when we say that, tossing it into the air, that means we're throwing it upward, right? Not outward, not horizontally, upward, straight up, okay? Tossing an object vertically in the air near the Earth's surface. Why would they put that in there? Where else are you going to be? We're always going to be near the Earth's surface, by the way. But this wouldn't pertain. This will not work if you're on the moon. You know, if you're out there on a spacecraft, if you're orbiting the Earth, if you're on Jupiter. No, you wouldn't. This won't work there. Okay? But anytime you're near the Earth's surface, this formula will work, and here it is. Okay? here is your position, and I'm going to go on and blow this up. Okay, here is your position. I keep wanting to say vector equation. Okay, S of t is equal to S0. Any idea what S0 would be? S is position. S0 would be where you are at initial, when you're at time 0. That's your initial position. Now, if I'm standing here in the room and throw the ball up in the air, and as long as I don't throw it too hard and don't hit the ceiling and wait for it to come back down, my S0 would be here. Now, you can designate that anything you want to. You can make it 0. You can make it anything. Okay. Now, if I did the same thing and reached my hand out the window and threw the ball straight up and then let it come down, guess what? Its final position is going to be something less than that. So it depends on where you want your 0 to be. If you want it to be from rest, but if say, no, you're on the second story of the building, so you're 4 meters up, okay, then S0 might be 4 meters. So that's whatever your initial position is relative to whatever reference frame you have chosen, okay? You get to choose your scale, where you're on the scale. If you're above the 0 position, that's a positive. If you're in a hole and throw it up, like someone says, you've been digging a ditch and said, someone throw me your shovel. So I throw the shovel up, vertically upward, then he might be at 0, I might be at negative. Okay, so S0 could be whatever your initial position is. What do you reckon V0 is?
Different starting point.
Second?
Is it like a different starting point?
Not a different starting point. What does V usually stand for? Velocity. That's your initial velocity. Okay? If I'm throwing the shovel up, then whatever speed with which I throw it, that's its initial velocity. If I'm throwing the ball up, that's the speed of the ball. If I'm throwing up my lunch, no, we're not going to do that. Okay, never mind. Okay. Okay, never mind. Okay. Now, Galileo found minus 1/2 g t squared. Does anyone have any idea what g is? Where did that come from? What about gravity?
That's what the G is for.
That's the what?
That's what the G is for?
Yeah, but what about gravity? Gravity is just a force. Is G a force? An acceleration due to gravity. Perfect. So guess what? Position, initial velocity, and your constant acceleration. Okay? Constant acceleration because you're near the surface of the Earth. If you were up there on the International Space Station, G would not be the same as it is here on Earth, okay? Because you're way away from the surface of the Earth, okay? If you're on the moon, different G there, not the same. That all depends, because it's a force, it's an acceleration. The acceleration depends on the mass of the object you're on and how far you are from the center. On the surface of the Earth, we're the same distance from the center. So anything near the surface, you're going to be fine. Okay. Now, why do you reckon there's a minus sign here? This is a plus, that's a plus. Why do you reckon there's a minus sign here? Say again?
Gravity is negative.
Gravity is always pulling downward. We said position, I was measuring from the ground or wherever, that's usually measured positively upward. Velocity, if I'm throwing it up, that was positive upward. But acceleration, due to gravity, is always downward. So that's why the minus sign's there. So G is the magnitude of that acceleration, negative is the sign. Now you might ask yourself, why is there a 1/2 here and not in those other places? Wait till Cal 2, okay? This is a integration constant, okay? So don't worry about that yet. Okay, now what we're going to do, I want to ask you to do, if we were needing to find the velocity of that same object that you threw up into the air, okay, how would you find this velocity? It's one of those questions. Take a derivative of what? Of s, exactly. Now think of it this way. Let units be your friend. S is position, which is going to be measured in feet, meters, miles, or whatever, right? T is what? Time measured in seconds or hours or minutes or whatever, right? Now when you take a derivative, how do you write that in Leibniz notation? Oh, hard question. How do you write a derivative in Leibniz notation? The first derivative. It's the only one we've done.
D over dx.
Say again?
D over dx.
D what over D? Okay. There's no x in here. Okay.
D over dt.
Okay, d what over dt?
D ds.
Say again?
ds.
ds over dt. And s you say was measured in what? Say again? No, time is measured in seconds. Say again? Meters. Okay, let's choose meters. It could be feet, it could be miles, whatever. And time was measured in seconds. So the s dt is meters per second. And what do we measure velocities in? Meters per second, miles per hour, furlongs per fortnight, whatever you choose, okay? That's going to be your velocity. So we take a derivative of s with respect to t. And what would that be? It almost rhymes every time. Okay, you take a derivative of s with respect to t. Please say yes. Okay. Do it. Okay, you said yes. Okay. S0 is what? Not necessarily zero, but it's your initial position. Is that changing? That means it's a constant. Right? And what's derivative of a constant? Zero. All right, good. Okay. Now, take the derivative of that term with respect to t, and what do you get?
0.
Really?
Yes.
What did you do with the v0?
Wouldn't that also be a constant? So
It's a constant, but this is in front of, like if you had 7t, what's the derivative of 7t? 0. All derivatives are 0. That makes calculus really easy, doesn't it? You know?
Well, if v0 is 0, then...
No, I didn't say v0 is 0. I said that's your initial velocity. If I'm throwing it up in the air, I've got to give it a velocity. If I'm just holding it here, you're right. The initial velocity is 0. It's not going anywhere. Okay? Its initial placement is S0, whatever it was at the beginning. Never going to change because I'm not giving any velocity up. We're assuming we're throwing it up. Okay? So therefore, we're going to give a v0 that's not 0. Initial velocity is not 0. So what's the derivative of v0t? v0. Very good. Okay? And then this next term?
Minus 1/4 g to the t.
Okay, where did you get the 1/4?
Where you just the power.
Okay, 2.
Shall I put to the 1/2?
Say again?
Wouldn't that go to the 1/2 or just to the t?
Okay. What do you do with the exponent? If that was 8t squared. It's what? It would be minus gt because you multiplied, not the pi, multiplied the 2 by 1/2. Right? So that gives you a minus gt. Drop that by 1. And sure enough, there it is. Holding my hand on the board too long, okay? The v of t is the derivative of s of t, ds dt, which is, that's a constant, so its derivative is 0. This is a linear term, so its derivative is its slope, remember, v0, and then 2 times 1/2 in this universe is 1, and not 1/4, and that would be minus gt. Now, let's see what that says. At time t equals 0, what would be your velocity? Looking at this equation here. At time t equals 0, what would be your velocity? 0. Second? 0. You don't want to throw the ball at all, do you? You're no fun at all. You don't want to throw the ball, okay? You're just going to stand there and hold the ball. Initial velocity is 0. It's not going anywhere, okay? If you throw the ball upward, if t is equal to 0, plug in a 0 here. And what do you get? v0, your initial velocity. Yeah, that's what it means to be an initial velocity. At time t equals 0, your velocity is v0. That's what we mean by v0, initial velocity. Okay. Now I feel like a dentist. Okay. So, as they describe in your book, where S0 is S at t equals 0, position at time t equals 0, v0 is v at time t equals 0, velocity at t equals 0, minus g is the acceleration due to gravity on the surface of the Earth. Negative because it's always downward, and we've chosen up to be positive. Okay, now, they do give you some approximate values for g. Whoops. G is approximately 9.8 meters per second squared. Is that a good unit for acceleration? Yeah. Change of velocity per change of time. That's acceleration. That's meters per second divided by seconds. That's what meters per second squared means. Now we call that the SI units. You might think of it as metric units, but they usually say that. But if you're in English units, then G is approximately equal to 32 feet per second squared. Okay? So those are the two common values for G on the surface of the Earth. If you happen to be on the moon, it's going to be a different G. You happen to be on Venus, you're dead. No, I'm sorry. I mean, you can't live on Venus. Okay. But if you could, anywhere else, it's going to be a different G. If you're too far from the Earth's surface, it's going to be a different value. Okay. Any questions? All right. Now, go back to look at this equation again. This is your displacement as a function of time. If I just ask you, which I'm going to ask you, what kind of equation is that? What kind of polynomial is this? Yeah, I just gave one thing away. It is a polynomial. What type of polynomial would you call that? Hint, maximum exponent of 2. Well, this is so long ago we've forgotten that. We don't need to remember that stuff, do we? Say again? The 2 is even, but this is odd, so this would be a neither function, if that's where you're going. This would be a neither, but what if you classified polynomial equations in different forms? Like this, I'll give this away. This equation right there, I'm going to call linear, because its maximum exponent is 1. Okay. You answered my next question, or you gave me multiple choice on my next question. That will graph as a parabola. That's what I was getting at. Thank you very much. But it's a quadratic equation. Maximum exponent of 2 is called a quadratic. Quadratic equations always graph to be parabola. Okay. So that's going to graph to be a parabola. Okay. And basically it's going to look something like this. Okay. Now, I'm just going to look at this parabola and I'm going to tell you what I see in it. Now first, this graph. This graph says this is a graph of displacement S measured in meters as a function of time measured in seconds, right? Now, can anyone tell me the initial position? $10 meters. There, starting at t equals 0, your height or your displacement is 10 meters. Okay. Now, sorry, I can't tell you the initial velocity. Okay. Can't tell you from that. Namely because the scale, look at this. It's not, maybe it is starting at 0 here, but you see this is 10 here, that's 2 here. Okay, so it's not scaled. In fact, here is 10 on the second scale, there's 10 on the displacement scale. So it's not a evenly scaled, but it's fine because those are different units. You can scale them any way you want to. So I can't really tell you that. But if you were going to estimate what the initial velocity was, what would you do? It's one of those questions. Take a derivative, okay. And what does the derivative tell you? Of what? The tangent line, exactly. So what I would do, I would try to draw a tangent line there at t equals 0 as close as I could to that, and then come up with an equation for it. And whatever its slope was, that would be the first derivative. Now, of course, I'd have to have some hatch points there and stuff like this to make it estimate. I'm not going to bother with that. Okay. Now, can you describe to me, now, you're not throwing the ball up in a parabola. No. You're throwing the ball straight upward. Straight upward. And it's going up as a function of time. See, time is this way, not an x-axis. That's time this way. So at time t equal 2, goodness, you got a good arm. It's, what, 80 meters up there? Wow. 2 seconds later, it's 80 meters up there. At 5.1 seconds, it's, what, 140 meters up there? What an arm, okay? At 7 seconds, it's maybe 110 meters up there. At 10 seconds, it looks like we're pretty close to being 10 meters again. Something like 11 seconds, I'm going to guess. 10.2 seconds, it's going to be more than that. Whatever, okay. So, you can just pick off where it is, but remember it's just going straight up and down. Oh yeah. For the first 5.1 seconds, it's going straight up, right? What happens at 5.1 seconds? Say again? What'd you say? Someone said it. It stops! Exactly. Because I can't throw it high enough that at some point up there it's going to stop. Okay? And when it stops, what's its velocity? 0. Okay? Now, what is the velocity? When you look at the parabola, that's the graph of the displacement. Velocity is one of those questions. Derivative of your displacement, right? And you just told me the velocity was 0. And what did you tell me earlier the derivative was? Slope of the tangent line. And you just told me at that maximum point, wherever it is there, when it stops, the velocity is 0. That means the slope of the tangent line is 0. And there is the place where the slope of the tangent line is 0. Okay? And they are telling you that's exactly 5.1 seconds. Okay? Nice. Anything before, from 0 to 5.1, the tangent line was upward. Pretty steeply upward here, not as steep there, not as steep there, went to 0 there, but then what happens on the way down? the way up, the velocity was positive. Then it stopped, and on the way down, the velocity is negative. Okay? Just like acceleration is negative down. And guess what the slope of the tangent line is? Negative. See how all this fits together pretty well, doesn't it? So the maximum height occurs when S prime, the first derivative of your displacement function, which is your velocity function, when that velocity function is 0, you're at maximum height. It can't go any higher. And it's on its way down after that. Okay? Now, let's do example 6. I think it may use this very, if it doesn't, we don't have another one for it. A stone is shot with a slingshot vertically upward, okay, with an initial velocity of 50 meters per second. Now, what does that stand for? 50 meters per second. What did they call it? I just read it. Initial velocity. What symbol do we give for that? Second? V0. Excellent. Okay, V0 is 50 meters per second. From an initial height of 10 meters. So what's that? That's your S0, initial displacement, or height. Okay? It says find the velocity at t equal 2 seconds. Okay? How in the world can we do that? Do you see a formula anywhere here? Not in the problem, is it? But if you flip back one page, flip back one page, flip back one page, do you see a formula there? In a little tote box down there. What is it? Okay, I'm going to flip back one slide. You see it? There is your position formula. Okay? Y'all got what it is? Okay? Tell me. No, let's do S. Let's do S. S of t, S0, t, minus 1/2, gt squared. All right. There is your position. Okay? A stone is shot with a... now, we know enough to start filling in, don't we? S of t is equal to, in this problem, 10. That's your S0. Second? Oh, okay, plus what? 50 t minus 1/2 9.8. Why do we use 9.8? Because this is in meters per second, that's in meters, and 9.8 is in meters per second squared. Get in the same units. And we did. Good choice. And then t squared. Okay? Let's clean that up a little bit. That'll be 10 plus 50t. Can you do half of 9.8? Oh, it's such hard math this early in the morning. What is it? Pull out those calculators. minus what? 4.9 t squared. There's your displacement function. Okay? But the question said find the velocity. So then we need to get the, and I know y'all are wanting to go right to that one, but I want you to get that one. What is your velocity function? That's ds dt. Perfect. And that is? A little louder, huh? It's what? Okay, yeah, let's use this equation there. There it is in t's. Okay, you're taking the derivative of 10 and you get 10. New calculus, I never have gotten that down real well, okay? Derivative of a constant is 0, so forget about the 10, okay? Go to the next term. 50 minus 9.8 t. Got it. Okay? And then what's your question here? Find the velocity at t equal 2. So v of 2. That'll be 2 seconds, I hope. They don't say that, but you're assuming that. What's t of 2? Tell me how to get it. Plug it in. 50 minus 9.8 times 2. Now, I'm going. Say again. Okay, that may be. Okay, you said 30.4. Is that what you said? 30.4. What units? Meters per second. Very good. Okay. Now, I wanted to point that out to you. Remember, your 50 was in meters per second. 9.8 was in meters per second squared. We didn't write it down. Let me write that down again. And that's what I meant to say earlier. The thing they didn't give you, but you assume, 9.8 meters per second squared. So you take meters per second squared, multiply it by seconds, because this is 2 seconds. That 1 second cancels one of these out, and you're left with meters per second. So your units are your friends. Keep up with them. Okay. So that's 30.4 meters per second. Now let's do v of 7 seconds. What would that be? Pretty easy. Say again? Negative. Okay, he went on to that'd be 50 minus 9.8 times 7. Okay, and that would be what? Negative 18.2 units meters per second. What does that mean? Second. Say it again. I can't hear well. 0.6. Okay, I'm sorry. My hearing is bad. Okay, 0.6. Okay. I'm counting on you people. Okay, thank you. Okay. What does that mean? Can you have a negative velocity? Yeah, it's on its way back down. It's past the 5.1 seconds. 7 seconds beyond that, it's on its way down. This is the slope on its way up. 30.4 meters per second. 2 seconds later. 5.1 seconds later, it's way up there around 130 meters high. And then on the way back, that's a strong slingshot, or a small stone. I don't know. On the way back down, now the velocity is negative 18.6 meters per second. Not quite as steep coming down there. If we went on over to the point directly opposite here, that would be the same slope as this on the negative. Okay, good deal. Does that make sense? All right. The B part says, what is a stone's maximum height, and when does it reach that height? Oh man, how do you get that? What is a stone's maximum height, and when does it reach it? Frankly, folks, the second question's the one that you do first. How do you determine its maximum height? What's true about the maximum height? What's 0? What is 0 at the maximum height? The velocity is 0. Here we have a velocity function right there, don't we? And so we set that equal to 0. And what do we get? What do we get? Can't we solve that little simple linear equation? Oh, no, we're in calculus now. We don't need to solve linear equations. Please tell me you can. Second. I like it. 9.8t to both sides. All right, that sounds good. So you get 9.8t, because these add to 0, is equal to 50. And then you're going what? Divide both sides by 9.8. And what do you get? T is approximately equal to 5.1 what? Seconds. Time is measured in seconds. That's how they got that too, by the way. So I told you the second question was easier to answer than the first. You got when it reached the maximum height first. You still got to answer that first part of B. What is the stone's maximum height? How can I determine that? To where? To the what?
To the Galileo's formula.
Oh yeah, okay, Galileo's formula. I couldn't hear what you're saying. Yeah, to the displacement formula. That's going to tell you the height at any time t. So plug in 5.1 there. So we basically are going to do S of 5.1 seconds. And that would be what? What was your S0? Second? Okay. This is the formula we're plugging into, right? 10 plus 50 times 5.1, that's your T, minus, okay, let's use this one, okay, 4.9, 5.1 squared. Let's see what that gets us. Calculator time. This time I don't object at all to you using that. I could do this and this, but that I get having headaches. So punch it in and let me know how high you got. I've been approximating that to be about 130. I bet you that's not exact, but what do you get? Say again? 137 what? Well, no, what I meant, if it's 0.6, then let's round that to 138. Is that what you said? Ooh, it didn't take. Okay. So round that to approximately 138. What units? Meters. That's height measured in meters. That makes sense. And that makes sense too because your S0 is in meters. This was in meters per second, but you multiply it by seconds, so that left you meters. And this was in meters per second squared. The 9.8 was. Half doesn't have any units in it, so 4.9 is still not meters per second squared. Multiplied by second squared, so second squares go out, you're left with meters, 138 meters. Is that what they got? They got 137.6. Okay, sorry about that. This is a math book. They don't really worry about significant digits. But in reality, the most significant digits you can have here was 2. So really, when we gave this as an answer here, it should have been 30. When we gave this as an answer, it should have been about negative 19. When we did this one, really, we should have said about negative 140. If you were trying to obey significant digits. But again, that's physics, not math. Okay? Math doesn't seem to care about that much, which I think they should. But anyway. All right, does that make sense? So you see, even though they asked the question in one order, what is the stone's maximum height and when does it reach it? Real easy to get when, then you plug that answer in and get where, how high. All right. Maximum height. Oh, this is, what in the world? Okay. Well, I'll use the slide. Okay, example 7. Okay. And by the way, I'm surprised to find this in a math book, but here it is. Okay? I give this in physics and physical science classes all the time. How important are units? Oh, who cares about units? Let's just give me a number. It's a math book, right? Look at this little blurb here. How important are units? In September 1999, I'll just give you a little bit of history on this. From basically the point at which the Russians sent up Sputnik. You remember? Oh, y'all don't remember that. Have you read about it in history? Okay. They got the first satellite to orbit the Earth. It was unmanned, named it Sputnik. Everybody got really upset because here the Russians, the Soviet Union, the bad commies, have something in space now. They could bomb us from space, you know. So we have to defend ourselves. So we started, like everything, to try to catch up with them, and that began the space race, if you've ever heard of that. Okay? So we started pouring money in. The federal government established, anyone ever heard of NASA? National Aeronautic and Space Administration. It was formed, it was funded big time. And they said, whatever it takes, let us know, we'll give you the money, catch up with them. Okay. So we started the space race, and for a while NASA was floating in money. I mean, they just, whatever they wanted, if they wanted to try something, they, yeah. So, yeah. Well, we finally caught up with, and guess what? The Soviets got the first man in orbit too. Boo hiss, okay? But we had one shortly thereafter. And then we finally passed them when we reached the moon before they did. Manned reached the moon. Americans stepped out there before the Soviets did. Whew, we finally got ahead of them. Well, Congress changed, and they said, you know, we're spending way too much money on NASA. Let's start cutting back. You're paying them to do everything. Here we have all these universities. Here we have all these national laboratories. We have a lot of people that we're paying anyway. Let's get them to figure out some of the stuff, not have to hire people to do all the calculations for us. And by the way, have any of you seen the movie Hidden Figures? Please see that. It is a phenomenal story. And it was right back when this stuff was happening. Okay? The space race. It was all over in the movie. And it's just an incredible, incredible story. Because you see, back then, could you hold up that little black box you were using? Or a white box, or whatever box it was? Did they have these back then? No. Did they have these back then? No. They had to figure all this stuff out, pencil on paper. Pencil on paper. And I tell you, calculations a lot more than 1/2 9.8 times 5.1 squared. Okay? I saw you. I said, go for them. They did it all by hand. And that movie is about some really brilliant women who could do it by hand. In fact, could do a lot of it in their head. Okay? So, so here we started, and we beat them to the moon. So Congress started saying, okay, too much money is being spent on NASA. Let's cut back, cut back, cut back. Let's farm it out to other people. So NASA started doing this, and that's where this comes in. September 1999, the 125 million Mars Climate Orbiter spacecraft was sent up. But you see, NASA couldn't afford, they didn't have the money to do all the calculations and planning for it themselves, so they did grants. and they said, somebody figure out how to launch it. You know, what's going to be required, the weight of it, all this kind of stuff, okay? Somebody else figure out how to get it out of Earth's orbit on a direct trajectory to Mars. That's not a simple problem, by the way. Mars goes around way out here. We're here, you know, we're sometimes close, sometimes far away. Someone figured that out. They farmed that out. Okay, you got us to Mars. Someone else take the problem of getting us from reaching Mars into Mars orbit. Okay? And then we'll go take it from there. So they farmed out these things of all these calculations and stuff to really good groups, and they knew what they were doing and everything, and perfect launch. Everything went so smoothly. And that's it does work. We can do it cheaper. And then when it was time to leave the Earth's orbit, it headed rendezvous with Mars perfectly. And then it took a turn. When it was supposed to start orbiting Mars, it turned toward Mars and crashed into the planet. Burned up in the Martian atmosphere before completing its scientific mission. According to Arthur Stevenson, NASA chairman of Mars Climate Orbiter Mission Failure Investigation Board, boy, talk about a government title, in 1999, the root cause of the loss of that spacecraft was the failed translation of English units into metric units. See, this first team was using metric units. The second team was using metric units. The third team assumed, because the second team didn't put the units down, they just assumed the third team was going to know what they were talking about. They thought they were dealing in English and they were dealing metric, but this one used English rather than metric because no one put the units down, and there went $125 million crashing and burning with almost no data collected. A big lesson learned, though. Okay? Now, I hope that one day you're successful enough that you can be in a position you could make a $125 million mistake. I hope you don't. And I surely hope you don't, because you forgot to put down the units. So always put down the units. Okay? So, anyway. That was my little soapbox. Okay? Because I'm a physicist by nature. Okay? By training too. Okay. So finding initial conditions. What is the initial velocity V0 is required for a bullet fired vertically from the ground level to reach a maximum height of 2 kilometers. So all we know, we're looking for V0. That's the unknown in this problem. Okay? What initial velocity is required for a bullet fired vertically from ground level to reach a maximum height, so we want S max, okay, SMAX, equal to 2 kilometers. Okay? Guess what, folks? That's all they've given us. Now, there is one more other piece of information we know, because it says from ground level, and we're assuming that ground is on Earth. With that assumption, what other piece of data do we know? Parameter we know? Y'all have mentioned it several times today. Say again? What about gravity? That's, what is it called? It has to do with gravity, but it has a physical meaning. What are you measuring with 9.8? Acceleration due to gravity is 9.8. Oh, it's just a number. Meters per second squared. No, you have to have those units, or else there goes your $125 million mistake, okay? Now, just with what we know, and by the way, there is one other piece here. It says from ground level. That also tells us something. What does that tell us? S0 is equal to 0. Ground level, that would be 0. That's where it's fired from, or shot from, or thrown from, or whatever. Yeah, a bullet fired vertically from ground level. Okay, so get all of it out of it you can. Okay? Now, does anything seem a little bit wrong with these data that we've got up there? Second? I can't hear you. And what about them? You mean the units are different? Right. So we need to either get the meters to kilometers or kilometers to meters. Anyone know how to do that? Is what? And how? Oh, that's what I was asking. What does, say again? 1,000. This is 2,000 meters. Kilo means 1,000, okay? 2,000 meters. So get all your numbers in the same unit. Now, I hope none of you know this, but on the streets, a kilo would be, it would be a measure of kilograms. A kilo is 1,000 grams, okay? Y'all, I'm glad you don't know that. Okay, good. Okay, stay off the streets. Okay, now, what we're looking for is maximum height. What you reckon we're going to use to get this? Yes, and what is that? S is equal to S0 V0t minus 1/2 G T squared. Okay, let's plug in the numbers we know. S0 is 0. Done with that one. Okay, so this would then be S of t, I should have put that in, is equal to V0t. We don't know V0. That's what we're looking for. V0t minus 1/2 of 9.8, 4.9 t squared. Okay. What initial velocity is required for the bullet fired vertically from ground level to reach a maximum height of 2 kilometers, or 2,000 meters. Now, we haven't used that yet. Okay? Okay, but what is 2,000 meters? That is a displacement, right? So let's put that in there. That's, okay. If we plug that in here, that's not quite going to give us V0, is it? Because we're still going to have a T in there. But how did we get rid of that T before? Guess what? It's reaching its maximum height. What else did we know? We knew what? Yeah. And so we do need to get the velocity function. And what is the velocity as a function of t? In relationship to s? It's one of those questions. It's the derivative of, so how you want to write that? You like it v prime or dv dt? You can do any form you want to. Tell me. dv dt, I mean ds dt? Okay, ds dt, which is equal to what? v0 minus, say again? I can't hear. Yeah, but what's g? It's right there. 9.8 times t, which I was hoping you were taking a derivative because that's what we're doing now, right? Derivative of V02 is V0, and the derivative of that would be 2 times 4.9 minus 2 times 4.9, negative 9.8. Yeah, got it. Now, what about that derivative at maximum height? What's the derivative at maximum height? Why? Because, yeah, that's where it stops. The V0 is, I mean, not V0, V is 0. So that would be 0. So at what time does that happen? We can solve that for t, right? What would that be? Y'all did it before when there was a number in there. You can do it now too, can't you? What's the first thing we did? Oh, yeah. What was it? Add 9.8t to both sides. I'm going to have to refer some of y'all back to to algebra here. Okay, so this gives us 9, because this goes to 0, 9.8t, I'm flipping sides here, is equal to V0. So guess what t is? What do we do next? Divide by 9.8. Divide by 9.8. These go away, so your t is equal to V0 over 9.8. All right. Now, we take this. We know what S max is. The maximum height is 2,000. And it's going to reach it when t is equal to this. That's equal to V0 times this t, V0 over 9.8, right? Minus 4.9 times V0 over 9.8 squared. Oh, what a joy, right? Okay with that? When we solve this, we're going to get V0, aren't we? Okay? So let's see what we get. 2,000 is equal, V0 times V0 is V0 squared over 9.8 minus, I'm going to do the 4.9 times V0 squared over 9.8 times 9.8. Now I'm doing that for a reason. I know it looks silly, but that's what 9.8 squared is, right? You just multiply it by itself. Here's why I'm doing that. It's not necessary. Y'all have calculators, but if I don't have a calculator up here, 4.9 will go into 9.8 twice, right? So that will then be, see, I didn't want to square 9.8 and then divide it into 4.9. If you do it this way, that's just 1 over 19.6, right? So this would be V0 squared over 9.8. I'm going to leave it just like it was. V0 squared over 2 times 9.8. Right? See, I don't need a calculator this way. Okay? Now, how can I get this to have the same denominator as that one? There's a subtraction problem of fractions. Y'all do remember that, right? Okay. How do you subtract fractions? You have to have common denominator. What do you reckon it's going to be? Okay, yeah. 2 times 9.8. So how do I make, this one's already 2 times 9.8. How do I get this one to be 2 times 9.8? Multiply it by 2. And if I multiply the denominator by 2, what did I better do also? The numerator by 2 as well. Very good. Okay, and now we got this same denominator, whatever it is, and that's 2 V0. I wrote it in the wrong place. Duh. Okay, V0 squared minus V0 squared over 2 times 9.8. Well, what's 2V0 squared minus 2 it's minus V0 squared? V0 squared. So this just is V0 squared. So guess what? I'm going to pull it up here. We got V0 squared over, let's go on and multiply it out, 19.6 is equal to 2,000. Right? Because that was equal to 2,000. Multiply both sides by 19.6. And I think that's going to be 392, and then a bunch of zeros. Huh? 2 zeros? Is that right? And then guess what we do? Take a square root. Take a square root of both sides, and V0 would be equal to I'm so glad we have calculators. Guess what? Those ladies were having to do that by hand.
197.
Say again?
197.98.
Let's make it 197.98. Let's make it 198. Approximately. 198 meters per second. Okay. And that's what they got. Good for them. All right. Now, that's theoretically. In reality, anything going that fast is going to meet a lot of air resistance. And we probably haven't taken into account air resistance. You would have to in this kind of situation. All right. Good deal. Any questions on that? Did you see how we did it? And you can do it again, right? Sure we can. Okay. And that's part of it right there. We got that far. All you do from this point here, multiply both sides by 19.6, and that's what we did, and then take a square root. Okay? And here's a little historical perspective on good old Galileo. Now, remember I said that someone could write a paper on Galileo. He's mentioned in the book here. He was a good mathematician in addition to being a great scientist. But guess what? This cannot be your source. You have to have an outside source, not the book. This can give you the idea, yeah, let's write on Galileo, but you need to get your source out of the book. And just looking at this, you also see that Newton's brought up here, so certainly Newton could be a source. Anyone already chosen Newton as a topic? So he's still open. Later, another great physicist was deeply puzzled, Albert Einstein. So he could be one. Now, I would say be sure you get some calculus involved. You can't go very far with Einstein without running into calculus either. And his general theory of relativity, that would be another potential paper topic. They keep mentioning principle of equivalence. I don't know if you can find enough of that to write a paper topic on, but you certainly could. Okay? The others certainly are in there. Now, by the way, Albert Einstein was one of the most brilliant people ever to live. Newton was another one, okay? Galileo wasn't far behind. But Albert Einstein occasionally had some math questions. He was a great physicist, but sometimes he needed a little help with his complex mathematics. Do you know who he turned to? Another woman, okay? Her name was Emily or something like that, but they called her Emmy Noether, Noether, something like that. I think she was German also. Einstein was German. Well, actually, he was Swiss, but he did a lot of work in Germany, so he, I think, had some German citizenship. Where did they both wind up? not in Germany. You know where Einstein died? In the U.S. And I think Emmy Noether died in the U.S. Does anyone know why they were here in the U.S.? Were they attending scientific meetings? No, they had immigrated. Anyone know why? They were both Jewish. Guess what this time was? Second? Yeah. Well, it was at the same time as that. They got out of Germany because they didn't have much future there. You know, Jews could not hold any kind of high position or anything else with Nazi Germany's anti-Semitic stuff, including the Holocaust and the work camps and all that kind of stuff. They got out while they could, made it to the U.S. So, sort of hard to say thank you, Hitler, but you know, we got some pretty great brains out of that because of his stupid. Shouldn't go. Okay, that finishes. Oh, here is an apparatus of the type. Your book shows balls rolling down an inclined plane. You see, here's the thing about Galileo. When he was doing these experiments that came up with that formula we just did, we mentioned not having calculators or computers. Guess what? They didn't even have clocks or watches at Galileo's time. So how in the world was he going to be able to measure time very precisely, especially for a falling object? Because that's what he was doing. So what he did, brilliant guy that he was, he started dealing with inclined planes. His time devices were not very good, but they could, if the time was a little bit longer, he could get a lot more precise. Dropping down like this, they weren't good enough. But with inclined planes, it made the time longer, and then he took a limit as you went to 90 degrees. Clever guy, okay? Because he had to use what he had. So this is one of the apparatus of the type that Galileo used to study the motion of falling objects. He couldn't do straight down because he didn't have a time device that good, but he did have devices that could measure a longer bit of time to a decent precision. Pretty incredible. All right, let's go back. Do y'all want to do the preliminary questions, yay or nay? The summaries there has all the things we did, you know, important formulas and stuff. Do you want to do the preliminary questions? It's up to you. You find them useful? No? Okay. I'll be glad to do them if you wanted to. So homework exercises are any of the odds 1 through 7, either 9 or 11 or both, and then any of the odds 13 through, boy, there's a bunch of them here, 13 through 37. Now, I wouldn't just do 1 or 2 of those. I'd do several of those, okay? And then do any of the odds 39 to 45. Those are all fairly similar. And then you can think through 47 if you wish. It's sort of a writing problem. But guess what? It has another person's name in it. Stephen's Law in psychology, okay? Wouldn't think you'd have something like that in a calculus book, but all fields use calculus. If that's an interest of yours, you could consider that as a paper topic. Then if you look at further insights and challenges, I don't require you to do these or anything, but I like to look at them. Very first thing there, the Lorenz curve. Well, who in the world was Lorenz? How did he develop this curve? It's used by economists, by the way. You know, not psychology, not mathematicians, but economists. But sure enough, there's calculus and economics as well. So you can write on that if that's an interest of yours as well. Okay, I'm trying to see if there's any others. Okay, I see none, so let's proceed. Any questions? 3.4. Let's move on to 3.5. As Is it going to do anything here? Okay, so far it sounds like it's doing something. Yeah, there it comes. Y'all need a break? Yes? Okay. I could kind of use one too. So we'll get the slideshow set up from current slide, and let's pause 3.4. Okay. Let's move on to 3.5. We've already, remember, when we're doing the acceleration, and we talked about change of velocity and acceleration. That was looking ahead to what we're doing here. We're going to talk about higher derivatives. Okay? You know, of course, I think I'm going to have to get my pen back. Okay? If you have a function f, we'll make it a function of x. Y is equal to f of x. Good old favorite from pre-calculus algebra. What's the only thing we can do with that? It's one of those questions. Take a derivative of it, of course. Okay? Now, there's several ways you can express that. You can say y prime. You could also say f prime of x. You could also say dy dx. You could also, whoops. You could also say df dx. Okay? All those mean the same thing, df dx. And f being a function of x. You don't have to put that in there, but you could. All those mean the same thing, and that's the first derivative. What is that telling you? What question are you answering when you do that? How is y changing when x changes? How is the function changing when x is changing? That's what a derivative is telling you. What is happening vertically when you're having change horizontally? That's what a derivative tells us. The instantaneous rate of change of your dependent variable with respect to, that's why we write it this way. Change of y over change of x. Change of f over change of x. That's what the delta means. The d means it's in the limit of delta. Okay? But then you get a new function then, right? This is some new function, f prime of x. Okay? Well, and by the way, this happens in physics all the time. The very example we had before. Well, the first things you measure in physics or physical science is the displacement from here to there. Okay? That chair used to be here. It got displaced over there. Well, that is a measurement. It went 5 meters, across the floor there. Well, I might say, well, did it do it real quickly or real slowly? In other words, how did that change occur over time? Otherwise, what the change rate, the time rate of change of that displacement over time? Well, that told me the speed of the chair as it went from here to there. That would be what your first derivative tells you. But then, like we did in that last problem, what if that speed wasn't constant? What if it started slowly and was increasing speed all the way there? Or increasing for a while, then decreased for a while? Well, then what you have, the time rate of change of that velocity. That would be the second derivative of this, because what you could do is, and this is what they're hinting at, then f double prime of x is going to be the change. Now, I was talking about time. This is change of f prime of x over x. Okay? That, whereas if f of x is a function of x, this is the time rate of change of that, then the the change of f with respect to x, then this would be the change of f prime with respect to x, and that would be what we call f double prime. And guess what? It has more than one notation too. You could call that y double prime. You could call it, like we just did, the f prime. The other would be d because you see this f, okay, d by dx of, what is f prime? df dx, okay? Now, this is that's what you're doing. You're telling the rate of change of this function with respect to x. And here's the shorthand they do for it. d2f over dx squared. Okay? That's what they give, d2f over dx squared. Okay? Now, you're not squaring anything. This just means you're using that operator twice. You used it once when you took a derivative. You're using now when you take a second derivative. So these are not, you're not squaring anything. You're just doing that operation twice. Like multiplying twice is what you get when you square something. Well, now you're doing the operation twice. Okay. Now, they haven't shown you that one yet, but I was just, since we were here talking about it, we do. So here's an example 1. Figure 1 and table 1. Here's figure 1. The next one will be table 1. So let's expand this figure 1 first. Okay. Now, what we've got here shows the number of cell phone subscribers, and they've all been in my classes, I think. No, I'm just kidding. Okay. C of T in the U.S. in year T, and then it says discuss C prime and C double prime. So here, this is a totally different problem. Oh, I'm sorry. Okay. The graph looks the same. I hadn't noticed it was a different graph. Sorry about this. Some of you don't have books, right? Okay. The graph looks very similar to this. Okay. I'll just change the numbers on it. In our book, this is, oh, yeah, wait. I'm going to have to shrink it. And this is going from 270 to 330. And that will be C, number of cell phone users in millions. From 270 million to 330 million users. Now, pretty sure this is, no, this is in U.S. Wow, okay. At year T. And then your years here are 2009, 10, 11, and 12. They just updated this, 11 and 12. Okay. Now, it's not the same values, but they're pretty close to it. Okay. So this is basically, this graph is a function of number of users as a function of time in years. Okay. That's what that is illustrating. Now, the question is, what is the first derivative of that? What does C prime mean? C prime. So used to writing F. Okay. C prime of T. What would that mean? Where C of T is the number of cell phone users, T is the number of years. What would C prime indicate? dC over dt, is that what you said? That was exactly what was going to be my hint if you didn't get there, but you did get there. Way to go. dC dt. Now, what does that sort of suggest to you? D meaning delta, or change in number of users per change in time per year, users per year. So that gives you the rate at which the number of users is either increasing or decreasing. In this case, it's what?
Cell phone users per year.
Okay, is it increasing or decreasing? Increasing. So that would give you what kind of a derivative? Positive derivative. Very good. So that's what deep C prime would be, the change of the number of cell phone users per year, and this graph shows it's going up, increasing over time. Now, what would C double prime of T tell you? What would you guess? Say again? Okay. Yeah, what I was getting at is this is the change of the rate of change. Okay? In other words, how is the rate of change changing over time? Do you see that? The CDT is the rate of change over time, number of users per year, but this is saying how is that rate doing? Well, what does the first derivative measure? Say again? Slope of what? A tangent line. Now these obviously aren't functions that have tangent lines, because all we have are discrete points. 1 year, the next year, the next year. But they've sort of drawn in line segments there. You can still estimate about what the slope of the tangent line would be. Now, what do you notice about this? There was the first, or something like that, then there, then there, then there. What does that suggest to you? Look at those tangent lines. They are, the first one here was pretty steep. It's still going up, meaning the number is increasing. But the rate of increase is not as fast as it was at the beginning. That's what second derivative says. The rate at which the first derivative is changing. The rate at which the first derivative is changing per year. And this looks like it's, the second derivative is negative. Meaning, it's still, the number is increasing, but the rate of increase isn't as great as it was a while ago. Okay? That's what it's telling you. We will show later that C prime was positive, C double prime was negative. Okay? Now, let's look at this table, and it's the wrong table too. But the graph was similar, so let's just use the table so I don't have to write all the numbers in. Now this is a different thing, but it was following the same pattern. And this is household energy consumption in Germany. Yeah, I want to know that. Okay. And the consumption is in millions of kilowatt hours. So that's the way we measure energy consumption. This is the yearly increase. So from 2002 to 2003, it went up. So the first derivative is positive, right? And it went up by that amount, so that would be about that would be an approximation of that first derivative. Okay? And from year 2003 to 2004, it went up again, didn't it? Okay? So there's still a positive slope there. Okay? Because it's increasing. However, the rate of increase decreased. Okay? So that meant the second derivative is now negative. Because final minus initial is now a negative number over time, 1 year. And then it's still increasing, but the rate at which it's increasing is still decreasing. And then in year 2006, the household energy consumption only went up by a little bit, still an increase, slight increase, but the rate of increase was decreasing. Okay? What's that? They knocked? Okay, I can't hear, so sorry.
those students in your class now? No, you don't have to. Yeah, we're going to have to look at that. Yeah. Well, yeah. When does it start? When does it start? Somewhere it starts. Yeah. Okay. Right now. Yeah, but today is Monday. So that you can. Yeah, but the 112, that has time. Okay. And that wasn't there. Yeah, I know. And they're both two spirits classes. Okay, both the full term folks. Oh, yeah, but y'all did 4 days a week. Well, I don't think you can do the 113 because it starts close to this, right? So you could do the 112, but that's not a problem. Right. Okay. So I would have to if well, see, the thing is, that wrong. So everyone's ultimately make a decision. They're cool. So I'll have to follow that. Basically, that is. So what I would say. It's already. Could you meet with the budget tomorrow? I know that you have. No problem tomorrow. Why don't we meet with the budget tomorrow and just, you just like you would if you were going to teach it, just tell the 113 class about the concept of possible. We'll probably have a different. Yes. Go there and just see if any other students show up. And probably we don't have to cancel that. I don't. Well, is it full page? But they. I'm gonna have to say, I'll call that. Yeah, but if you don't know.
All the administration is off on a retreat, and that should have been handled by them, but they're not here, so I have to handle it. So. All right. So you see what's going on here? First derivative positive, meaning it's increasing function. Second derivative negative, because the rate of increase is decreasing. So that's what we mean by second derivative. Okay? Now, is that fuzzy or is it making sense? Okay, no response. Okay, all right. That was example 1, by the way, is looking at those graphs. The old thing had different graph, but the shapes and everything were the same. Let's do example 2. Wait, okay. I guess before we go to the example 2, not only do you have a df dx, okay, you could take a derivative of that like we just saw and call it d2f dx squared. But guess what? You could say, well, how is that one changing? And that would be a d3f dx cubed. Now these are all d's there. Sometimes I get sort of sloppy there. You can go further. Now most of the time d fourth f dx fourth. That's the notation. That's kind of the Leibniz notation for this. And you can go on as many derivatives as you can take. Okay? Most of the time we don't, but you could. Okay? Now, they're not bringing this up yet, but it's going to have to be approached here. And it will be, yeah, it is in that next table. So let's do example 2. So let's calculate f triple prime. Now that means d3f d, what is your variable here? X squared, x cubed. F triple prime at minus 1. That's what we're looking for. For f of x is equal to 3x to the 5th minus 2x squared plus 7x to the minus 2nd. Huh. Can we do that? How do we do it? Take a derivative. Good answer. Take the first derivative first. So f prime of x is then what? A little louder. 15x to the 4th minus 4x minus 14x to the, nope, you subtract, negative 3. Always are subtracting that one. Okay? There's your f prime. Let's do f double prime. And notice we keep the x's in there. Don't plug in the minus 1 until you get to the derivative you need. Because you plug them in now, they come to you a number, the next derivative is going to be 0. So don't do that. Okay? What's this one? 60. X to the 3rd. And here's Jasmine. Okay, next. Minus 4. Hey, that's not 0? Never mind. Okay. Next. Plus 42 x to the 4. You got it. Now let's do f triple prime of x. And what's that? 180 x squared. Yes, that one is 0. Good. Minus 168 x to the negative 5th. You got it. Now we got our third derivative of x. Now we plug in the minus 1. So f triple prime of minus 1 would then be what? 180, because negative 1 squared is 1. Okay? Okay, and then you said what? Minus 0. Is that what you said? Okay? When you put a negative 1 in for x, okay, let me...
I kept the exponent. Plus 168.
Huh? Plus 168. Now, in this case, I do want to go back. Let's call this 180 x squared. We can do that. Minus 168 over x to the 5th. That's what x to the minus 5 stands for, right? And when you plug that in, I think you'll see. Plug the minus 1 in for x squared, x here, you square that, you get plus 1, so you get 180. And then minus 168, but then when you plug in a minus 1 in the denominator here, erase it to the 5th power, what does that come up to? Negative. So that minus changes that. I'm glad they didn't ask to do that for x equals -3, aren't you? -1 I can live with. 1 I would like better. 0 normally I would like, except you couldn't have 0 that happens because 0 is not defined in the denominator. So, now, did you give me an answer though? I guess you didn't. 348. Good. Excellent. Okay? All right. Now, was this a polynomial function? Say again? I couldn't hear. Yes? What makes a polynomial function? The requirements are, it looks a lot like that. The requirement is that the exponents can only be whole numbers, no negatives, no fractions, no decimals, no irrational, only positive integers. That's the negative integer. So this one was not a polynomial. If you left off that term, yeah, that was a polynomial. If that had been just an x there, that would have been a polynomial. But with a -2 there, it's not a polynomial. The polynomials have, as they say here, a special property. That's what this table is showing. Now, it's also showing something else. But let's do derivatives of x to the 5th. Now that's a polynomial. It's only one term, but it's positive exponent, so you're okay. And a whole number exponent. So the function itself is x to the 5th. Let me go and blow this up so you can see it better. Okay. If your function is x to the 5th, your first derivative would be what? 5x to the 4th. Second derivative? 20x cubed. Third derivative? Fourth derivative? 120x. Fifth derivative? 120. Sixth derivative? 0. There is the feature you were reading ahead, weren't you? Okay. There is the feature of polynomial functions. You can take as many derivatives, okay, as you have the maximum exponent, the degree of the polynomial. The next derivative and all past that are always going to be 0. Okay? You can keep taking them, but they're all going to be 0 from there on. So that's sort of a special feature of a polynomial function. Now, if you have those negatives in there, negative exponents, they go on forever. They never reach a 0. Okay. The other feature of this is when you're using the Leibniz notation, this would be d6f over dx to the 6th. Okay? d6f over dx to the 6th. Okay? When you're using the prime notation, you can do a single prime. You can do a double prime. You can even do a triple prime, but guess what? They don't want you to keep doing 4, 5, 6, 7, 8, 10, 15 primes. You lose count. I can kind of keep up with 3. After that, they start running together. So what they do, past 3, they put the 4 in parentheses. Now, why do they need parentheses?
To keep it separate.
From what?
From the action.
Okay. If you had put f to the 4th,
x, that would have been taking x fifth and raising it to the fourth power. So without the parentheses, that means raising that function to the fourth power, multiplying by itself 4 times. With the parentheses, that means derivative, the fourth derivative. So that's the notation. For prime notation, past 3, you start putting the number of derivatives in parentheses. If you leave off the parentheses, then it's confusing and you think it's raising the function to a power. So in parentheses, that means you're taking that derivative.
Okay? All right. So, I don't think they have a slide for example 3, so let's do example 3. I think I'm going to clean the... Any questions before I clear this off? Okay. Calculate the first 4 derivatives of y is equal to x to the minus 1. What's the first one? y prime, let's call it that, is equal to negative x to the negative 2. Good. Y double prime would be 2 next to negative 3. Very good. Y triple prime would be negative 6 x to the minus 4. What do I call the next one? How do I write it? In parentheses. The fourth derivative of y would then be 24 x to the negative 5th. Y, parentheses, 5. Second. I think it's more like 120, isn't it? X to the minus 6. Okay. Now, I'm going to write it a slightly different way, starting with y triple prime. That would be a minus 3 times 2 times x to the minus 4, right? And this was a 4 times 3 times 2 times x to the minus 5. And this one was a 5 times 4, a minus 5 times 4 times 3 times 2, x to the minus 6, right? Because every time we multiplied by the previous thing, 2 is 2 times 3, or 3 times 2, then 4 times 3 times 2, times 5 times 3 times 4 times 3 times 2, 6, yeah, 5 times 4 times, yeah, okay. Does anyone know what this notation is? Have you ever heard of the term factorial? Yay or no? No. Okay. Give me a number. Any number. 9. 9 factorial is defined to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Right? That's what we mean by factorial. Any number factorial. And by the way, those numbers can only be integers. Positive integers. In other words, natural numbers. You don't need to know this now, but of course 1 factorial would be what? 1. And you don't need to know this now, but there is a little rule. 0 factorial, strangely enough, is also 1. You don't need it now, so don't even go there. Okay, but that's, if you ever deal any with probability, you're going to hit that. Try to avoid probability of all costs. Okay, so that gives us another way to express the derivative of this, which derivative it is. Okay? So here is a generalization based on what we've got so far. Y to the nth, right? Now, I want you to tell me if you see any other patterns here. Plus, minus, plus, minus, plus, minus, right? Yeah. And the y by itself, sometimes we call that the zeroth derivative of y. In other words, it's just a function. So if it's an even derivative, it's a positive number, right? If it's an odd derivative, it's a negative number. Now, how can we write that shorthand mathematically? I think I've told you this before, haven't I? I think one of the requirements to be a really good mathematician is to be just a little lazy. Have I ever told you that? Okay, I thought I had. And any of you qualify? I don't think so. Y'all are all hard workers, right? But you can still do it. It's just, you may have to work a little harder. Okay? Now, so to be a good mathematician, find an easier way to write this than every other number or every odd number. Yeah, and here's how they do it. If you want an odd number, do well, I was trying to think the best shorthand for it. Yeah, -1 to the nth. That would do it, wouldn't it? When n is an even number, this is always going to be plus, right? When n is odd, it's always going to be minus, right? So that's how we take care of the sign. So that gives you the sign. The coefficient, notice here, the fifth derivative is 5 factorial, the fourth derivative is 4 factorial, the third derivative is 3 factorial, the second derivative is 2 factorial, which is 2 times 1. First derivative is 1 factorial, which is 1. The zeroth derivative is 0 factorial, which is 1. Okay, so sure enough, this is n factorial. That gives the coefficient, and then you do x to the minus, okay, n plus 1, right? Because if it's a fifth derivative, that number is 6. Fourth derivative, that number is 5. But it's always a negative number. Third derivative is 4. So that's how you can express the nth derivative of x to the minus 1 in a shorthand notation. Okay. You don't need to know that necessarily now. That's not a necessity. Now they do one other thing here. I like it that way. They do it this way. -1 to the nth, n factorial, x to the minus n minus 1. They distribute the minus sign across the parentheses. I like it better the other way, but that's true this way too. Okay. And basically everything I said about factorials, they're in the little marginal note that they have there. So let's move on to example 4. I don't think we have a slide for that either. So let's do that on this slide too. Can I erase all this? Okay. Calculate the first 3 derivatives of this. F of x is equal to x e to the x. Okay. I hope all of you do remember how to do the first derivative of that, right? What is that? What rule do we use?
Not a power rule. That would be a power rule if it was x to the nth. That would be raising it to a power. In fact, that previous one was a power. It was just -1 power. This is two functions. What are they doing to each other?
Co-product.
Yeah, it's a product rule. These are multiplied together. So we're going to have to do the product rule. Now, someone needs to remind me what the product rule is because I forget so easily. So what is the product rule? Say again? Okay. You may be right. I'm not hearing well.
Would be first derivative times the second plus second derivative times the first.
Okay. Okay. You got the right idea. You're using the wrong words. Second derivative means f prime, double prime. But it's the first function times the derivative of the second plus the derivative of the first times the second. Is that what you were saying? Yeah, I thought so. Okay. All right. So tell me what it is then. You can do it in any order that you want to. I don't care. Either one of you. All of you. Anybody. Okay, x is the first function times the root of the second would be e to the x. I like that one. Okay, but then you got to do plus one e to the x. Yeah, that's it. Okay, what he did was the first times the root of the second there, plus the second times the root of the first. The root of x is 1. Okay, good. We got that. Didn't take too long, but we got it. Okay. Now let's do f double prime of x. Okay. You got two terms here. The first term is a product. It's not just any old product. It's the very same product we had before, right? Okay. So that would be, derivative of this would be exactly that whole thing. The derivative of just the first term is going to be exactly what we had before. X e to the x plus e to the x. Now we got to do derivative of the second term, which is plus e to the x. Now we can simplify that a little bit as x e to the x plus 2e to the x. Got it? About the third derivative, f triple prime of x. I think that's as far as they wanted us to go, wasn't it? Calculate the first three derivatives of this. Okay? Okay, let's go over here. Yeah, say again. X e to the x plus e to the x. That's that first derivative again that we had before. Plus say again? 2e to the x. Is that what you said? I thought so. Okay. Now, can we simplify that any? X e to the x plus 3e to the x. Now, the second part of this, then determine a general formula for f sub n, the nth derivative. I said sub n. The nth derivative of f as a function of x. Okay? Now, let's go back and see if we can simplify a little bit. Okay? What do you notice about that first one? What could you do to simplify that a little bit? Say again? I thought someone said the word. What's the F word? Oh, yes, good for you. Okay. And what might you factor out of that, those two terms? E to the x times x plus 1. Very good.
Could you simplify that second one any? And e to the x, I'll buy that. And what do you have left? X plus 2. How about that third one? E to the x, x plus 3. Okay? First derivative, second derivative, third derivative. What would the nth derivative be, do you think? E to the x, x plus n. Perfect. You may be a little lazy. I'm beginning to wonder, okay? All right. Would you be? No, never. Okay. All right. Make sense? For some reason, they put n plus x, e to the x. It doesn't matter, okay? n plus x, e to the x. And there again is just one more reason why I really dislike those computerized homework exercise packages. I mean, they have some good to them, but the thing is, if you had written this as the answer, it would have said no. If you had written e to the x, n plus x, it would have said no. If you'd have put x plus n times e to the x, it would have said no. Wrong answer, wrong answer, wrong. Every one of those are correct answers, but they were looking for that one. Okay? So that's why I really don't like those packages, because they'll tell you something's wrong when indeed it's right. It's just, especially in calculus, there's so many ways, very equivalently correct ways to write the answers. Okay. Good deal. All right, let's look at example 5. And I do believe we may even have a slide for this one, so let's see. Find the acceleration a of t. That's what we're... I can't write. That's the acceleration function, a of t, of a ball tossed vertically in the air from ground level. Okay, from ground level, what does that tell you? S sub 0 is equal to 0. As soon as you see one of those key phrases, jot down what it means. Tossed vertically in the air from ground level at an initial velocity of 12 meters per second. What does that tell you? V sub 0 is equal to 12 meters per second. Very good. Okay? Now, there's one more thing you can write down for me, because here's an assumption. When it says from ground level, what ground do you reckon that's talking about? Earth. Okay? If you assume the Earth, then what else can you write down for me? G is not gravity, it's the acceleration of gravity is 9.8 units, meters, second, squared. Accelerations are meters per second squared. Okay. Now, why did you choose 9.8? Because your velocity was in meters per second, so you want the gravity, acceleration due to gravity to be in meters per second squared, and the number for that is 9.8. If that had been feet per second, then you would have to do 32 feet per second squared. Okay. All right. It says find the acceleration. How would we begin this? Tossing a ball into the air, strictly vertical motion. Yes. Galileo's displacement, and how does that go? S of t is equal to S0 V0t minus 1/2 gt squared. Perfect. Okay. We're looking for a of t. Can we get directly from S of t to a of t? The key is no, directly, no. What do we have to do first? Take a derivative, very good. And what does derivative ds dt tell you? It has a name before it of its own. I think you were about to say it. That's the velocity of t. That's what ds dt is v of t. And what would that be? Derivative of S0 is? Derivative of S0 is 0 because it's a constant, okay? How about the next term? V0, the initial velocity. When you 1 times V0 is V0, t to the 1 minus 1 is t to the 0, which is 1. Okay, so that's that. Next, minus gt. Got it. Okay? That gives you v of t. What we're looking for is a of t. And what is acceleration? How is it related to velocity? One of those questions. Take a derivative. dv dt is equal to a of t. And what would that be? Second? 12. Is that what you said?
12 v is 0.
I'm sorry?
You're plugging 12 v is 0.
Okay. But the thing is, you're taking the derivative of the v. And the derivative of v, that's v. You take the derivative of a constant, it's 0. Okay. Next. Hike. No, never mind. What? 1? How'd you get it? Okay. When you take the derivative, the t to the first goes to t to the 0, which is 1. So this is just negative g. Because that's coefficients of 1. Take a derivative, and you just get negative g, which is negative 9.8 meters per second squared. And of course, the only acceleration of that thing is the acceleration due to gravity. That's the only thing acting on it. Okay, but find the acceleration a of t of a ball tossed vertically into the air, ground level, initial velocity of that. How does a of t describe the change of the ball's velocity as it rises and falls? How is that velocity changing? By the same amount every second. It's a constant acceleration. So, let's say we threw it into the air at 12 meters per second. Now I'm going 12 meters per second. 1 second later, because its acceleration is a minus 9.8 meters per second, so 1 second later, it would reduce that by 9.8. So that would be what? 2.2 would be its meters per velocity upward. And it won't go but a little fraction of a second before it starts coming down again. When it does start coming down, its acceleration is still minus 9.8 meters per second. It changes its velocity, whatever its velocity is, reduces it by 9.8 meters per second every second. So the next second, it would be another minus 9.8. So after 1 second, it was 2.2. Subtract 9.8 from that, and you get negative 6.4. So now it's going downward at 6.4. So every second is changing its velocity by the same amount, which is its acceleration. Okay? So the acceleration is the acceleration due to gravity.
Okay? As the ball rises and falls, the velocity decreases from minus 12 to minus 12 at a constant rate of minus g. Now, it didn't go just in 2 seconds. It reached the minus 12 in 2.45 seconds. You can figure that out yourself. This is the graph of the height of the ball as a function of time. That's a good old parabola, right? Now, it shows it intersects here at 2.45. It didn't show you how it got that, but you could get it. The velocity starts as positive, it's a little less positive, finally goes to 0, then it's negative, 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 until at that point here, it's minus 12. So it's down here. Well, the slope of that line is your acceleration. And that slope is minus 9.8. Okay? Constant acceleration. And I'm afraid for the zipping, it sounds like we must be out of time. Okay, so let me, before we lose you, I know I brought in a pencil. Oh, you did. Okay, that's all right. I've got another one up here. Okay. All right, thank you. Okay, it's perfectly fine. This doesn't have much of a eraser, but if you want this one, somebody left it in the room earlier. Okay, we ended this there. We'll start with this graphical insight next time. Okay? And then you get something to mark that. Homework exercises here. Try any of the odds 1 through 15. Try any of the odds 17 through 25. Try 27. Yeah, you can do 27. We did one like that. Or 29 if you prefer to do that one. Or both if you want to. And then any of the odds 31 to 35. Try 37 and 39. We do as many of the rest of them as you want to. Some of them we may not have gotten to yet. We'll pick up the rest of those next time. Good deal. Any questions? Okay. One more thing. And by the way, I think, yes, I received the first paper in today for this class. I may have actually received the first 2. Now I think it's just the first one. Okay. Way to go. Glad it's here. The rest of you, follow the lead. The floodgates have been opened. Let's start having the fourth now. So have a good weekend. That means working on calculus will make it a good weekend, won't it? Yes. Good deal. Thank you. Good deal. Thank you. Oh, second paper in. Good deal. All right. Good deal. Thank you. What's that now?
If I'm like planning on going to the office hour,
Right.
Do I have to make an appointment?
No, no. Just any time that's listed as an office hour.
So
Now,
it will be tomorrow?
Yeah, actually, my only blocks of office hours are on Tuesday and Thursday.
Okay, but yeah, it works for me tomorrow. So
Yeah.
What is it exactly the time?
10 to 12
10 to 12.
and 3:30 to 5:15
Okay. So 10 to 12, your office
is okay. Let me get
I
this.
think I know. Like